Hello again. Today we're going to be talking about the intuitive definition of a limit. In the last couple of videos, we've been talking about slopes of secant lines and about how we make 2 points get closer and closer together to get the slope of the tangent line. Limits are also going to be limits are going to be necessary to do the type of calculations that we were doing before, but without using a calculator. And this is a precursor to understanding the definition of the derivative. It's going to involve a limit. So I don't want to give you the mathematical definition of the limit because it's really not required. You can understand it sort of in an intuitive way, which is going to be much better. I will eventually explain what the mathematical definition of a limit is, but in most calculus courses, it is usually just brought up, mentioned, and then not used because it is very difficult to actually use the actual definition of the limit. And it's usually taught in courses beyond calculus. It just depends on the teacher as how important he feels the actual definition is. But anyway, we want today to get an intuitive definition of the limit rather than the exact mathematical definition of the limit. Okay, so for example, let's say we have a very simple function. This is a straight line, and it passes through the point 2, 2. We are going to say that the limit as x approaches 2 of f of x equals 2. What this is saying is that as your x-coordinate on your graph gets closer and closer to 2, your function, or in other words, the y-coordinate, is approaching a height of 2. So that we're heading there. Okay, now, one thing you don't want to mistake is you don't want to confuse what this limit is with where the point is. Because let's say that I moved the coordinate point that used to be at 2, 2, and I moved it up higher, like let's say to 4, like that. This does not change the value of the limit. The limit only cares where the function is heading towards as x is approaching 2, not at 2. Okay? So, like as we approach 2 from this side, we're approaching a height of 2. When we approach x equals 2 from this side, we're also approaching a height of 2. And so this limit is going to be 2. Okay? It doesn't matter that the point is up there at 4. It wouldn't even matter if this point weren't there at all. This limit would still be 2. Okay? So it's where the function is heading towards as x is heading towards 2. That's very intuitive or non-mathematical description of a limit. Okay, let's look at another couple of examples. Okay, so let's talk about this function. This function is sort of composed of little teeny pieces. I could probably write it as a piecewise function, and I'll talk about piecewise functions later. But let's talk about the limit at a couple of points on this graph. Okay, let's talk about at x equals 1. What is the limit as x approaches, negative 1? What is the limit as x approaches negative 1 for this function? Okay, as we approach negative 1 from the left or the right, going to the same height, 2. So you would say that the limit as x approaches negative 1 of f of x equals 2. Okay? What about at 0? 0 is also going to 2. So you would say that the limit as x approaches 0 of f of x equals 2. But at 1, we have something weird going on, because from the left side we would be approaching a height of 2, but the right side would be approaching a different height, 0. In this case, where we have this jump, the limit's not going to exist. So you would say that the limit as x approaches 1 of f of x just does not exist. I'll abbreviate that with DNE for does not exist. So sometimes these limits break and don't give you any values. And there are a couple of different cases in which that can happen. This being one of them where the graph takes a sudden jump in values as you cross a certain number, and therefore the limit from the two different sides are different. And another common example would be when you have vertical asymptotes. Let's look at an example with vertical asymptotes. Okay, so here is a simple function, f of x equals 1 over x. This is what the graph looks like. And if you were to try to compute the limit as x approaches 0, well, as x gets closer and closer to 0 from this side, it goes up forever. It doesn't go to any value, not a real number value. Same thing if you try to approach it from this side, it would approach negative infinity. And in fact, I'll talk about limits that go to infinity in another video, probably the next one. But for now, we'll just say that this limit doesn't exist. Okay, so in order for a limit to exist, as x approaches this number from both sides, both the heights from both sides have to approach the same value, some real number value, not infinity. Okay. Let's do an example using a function rather than just using a graph. Okay, so let's say we're trying to compute the limit as x approaches 2 of f of x, where f of x is x squared plus x. Okay, well, we really don't have any rules about this, so I said I was going to do a function next, but really with this intuitive definition, it is better to look at a graph. You know that x squared plus x is a parabolic function. So the graph is going to look something like that. And at x equals 2, you would get 6. And we know that parabolas are like unbroken, smooth, and continuous. And so as x approaches 2, you can see from the left and the right side, it's approaching a height of 6. So the limit as x approaches 2 of f of x would be 6. But what if we had a messier function? Let's do an example using a piecewise function this time. Okay, so this is the piecewise function I've chosen, f of x, x minus 1, if x is less than 0, f of x equals 3 at x equals 0, and f of x equals x squared minus 1 if x is greater than 0. Okay, once again, let's sketch this. Oh, and I'm interested in the limit as x approaches 0. So that's the limit I want to solve. So I need to sketch the graph near x equals 0, and then we can just look at the graph and see the answer. Okay, so here is a sketch of the graph. It's linear over here on the left side. At x equals 0, we have this funny little point at 3. And then over here, we have part of a parabola. And together, this makes up our function f of x. So if we're looking at the limit as x approaches 0, well, from both sides, it approaches a height of -1. Remember, the value at the point doesn't affect the limit. The fact that f of 0 equals 3 is sort of a completely separate problem. So when x approaches 0, our function is approaching -1. If they were to ask you, what is f of 0? f of 0 is a completely different value. F of 0 is 3. Okay, so this is about as far as we can go with our intuitive definition of a limit. But now you know about what a limit is doing. It is trying to evaluate what your function is heading towards as your x-coordinate is heading towards a certain value. And you can do that if you can sort of just look at a graph. You can pretty easily figure that out for most graphs, unless they get really messy as you approach those numbers. In our next video, we're going to be looking into limit formulas, having a way to compute limits without having to just look at the graphs. Oh, and by the way, if you have any questions or problems you would like me to look at, feel free to leave comments down below. And if I have time, I will look at them and try to answer any questions that you send me. All right, have a good day.